you've not seen before, right? Like greedy algorithms. You've not seen homework problems on greedy algorithms yet. So try to at least look at homework 3 before the midterm. And in case you guys forgot, so we'll have a midterm exam next Thursday. And so all of you have to show up in class to take the exam. And this will, this will count towards you. All right. So we'll just basically cover everything until what we do today and on Thursday, and that will be the syllabus for the midterm exam. And yeah, it's not something to really stress about, but if you want, I can put out the past finals and past and solutions to those finals as well. Okay, so it'll be a little easier than the finals. Usually for the finals we have 2 hours. Okay, but here it'll only be like 1 hour 15 minutes, so it'll be a little bit easier. But it will at least give you a sense of what kind of things. Okay, actually, yeah, the course web page from last year also has those if you just want to do that. Alright, so quick recap. So we were doing greedy algorithms the last couple of lectures. And the reason I have this slide is because last time I forgot to do this other standard examples for greedy algorithms. We did a few examples. We did this example of minimum spanning tree. We did something about scheduling jobs, okay, and you'll see a bunch more in your homeworks. Okay. And we also saw our first approximation algorithm. We said that for the set cover problem, if you do a greedy algorithm, you do no worse than some log n times the optimum solution. So that was the first example of an approximation algorithm. Today we'll see another. And yeah, so I did want to mention a couple of other standard examples of greedy algorithms. So one is finding the basis of a vector space. So maybe all of you remember like this basic thing from linear algebra 101, right? So how many of you remember what a basis is for a vector space? Remember, how many can define it off the top of your head?
So, yeah, I think it's like the analysis of the vector to the x-axis, to the y-axis, and to the z-axis. Is that not the same?
No, that's something else. Yeah, so okay, one particular basis for 3-dimensional space are the x, y, and z axes. Okay? But in general, if you have a bunch of vectors and think of them as being high-dimensional space, then you say that a bunch of vectors are linearly independent if no vector in that bunch can be represented as linear combinations of the other guys. So that's and the largest such subset is called the basis. Okay, so if you think about it, this is the problem. I mean, it's like asking, I give you a bunch of vectors, find the largest subset so that no person in that subset can be expressed as a linear combination of the others in that subset. Okay, so it's like a greedy selection process. So it turns out that here a simple greedy algorithm where you just keep adding vectors one by one as long as they are not expressible as combinations of the other guys. So that turns out to be an algorithm that works. So this is one of the canonical examples of greedy algorithm. And there's also a sense in which this is, I mean, almost all greedy algorithms can be expressed like this. Okay, so this is called matroid theory. Okay, so we don't have time to get into that in the class, but this is a very nice area. So in some sense, all problems in which greedy algorithms work can be expressed as something to this effect. Okay, so yeah, so that's something nice to know. Another classic example, which some of you may have seen in undergrad, is this of Huffman encoding. How many of you have seen this example? Yeah, fair number, yeah. So this is another standard example of a greedy algorithm, but it's somewhat non-trivial to show that it works out. Okay. So it's about how you succinctly communicate information when you know that certain letters are used more frequently than others. So that's the general idea of it. So yeah, and there are lots of other algorithms, mainly because it's such a natural algorithm that you use it for all problems. Alright, so that's what I wanted to say just before we go there. Yeah, in last class we started looking at local search, and we said that the general idea in local search is that you start with some solution, some feasible solution, and you try to improve it by moving to nearby solutions. So that's the general goal in local search. That's why it's called local, because you move to nearby solutions. And you stop if no nearby solution is better. And what nearby means depends on the problem. Okay. And yeah, and we said that the only way local search solution gives an optimal solution is if you have this condition that any local optimum, which is something that's optimum in its neighborhood, is also globally optimal. Okay, and we said that one canonical example of this is this class called convex optimization. And we just very briefly saw what it meant. Alright, so that's that. And then we started looking at this problem called the matching problem. Okay, and here it's a very simple question. So you have n children and n gifts. And child I has some happiness value associated with gift j. So if the child I gets this gift j, then he or she sees a happiness of some vij. Okay, let's say it can be quantified perfectly. Alright, and now the goal is you want to find an allocation which is assign one gift to each child. Okay, so that the total happiness, which is the sum of all the happiness values of the children, is maximized. Okay? So you don't care so much about individual children's happiness, you care about the total. So this is the problem. In fact, there's a version of this problem called the Santa Claus problem, where every person wants to be happy. I mean, you want to maximize minimum of the happiness, but that turns out to be much harder. Okay, so this is much easier. So you just care about the total happiness. Alright, so we saw that there is a natural local search algorithm for this problem. Right? So actually one thing that we also saw was that greedy really works poorly. Again, this was an example where if you started out assigning with one child, let's say you go in the order of children, and this is gift 1, this is gift 2, and let's say 2 had a very high value for gift 2, we started out by assigning child 1 to their best gift. So this is 1. So in this simple example, we saw this natural greedy algorithm where you just go in the order of the children. For each child, assign the best unassigned gift so far. And this is a greedy algorithm. Right? It builds the solution one by one. And this solution is very bad because if you start with 1, then you would assign gift 2 to child 1. And then child 2 loses out on this really great gift for this one. So this is the example we saw last time. And then we said, okay, so in this example, after the fact, you could have realized that, oh, if I had swapped the gifts for 1 and 2, I could have really improved the total happiness. And the question is, can you make these kind of adjustments in general? This suggests a natural local search kind of algorithm. That you come up with some assignment, and you try to see if swaps improve the solution. So this is where we stopped last time. Okay. So for every pair, I start with some solution, and for every pair ij of children, check if swapping the gifts improves the solution. So make the swap and continue as long as there are no swaps that improve. So Very simple algorithm. And note that this takes, actually local search algorithms can sometimes be slow. So can you guys see how long this procedure takes?
Could it possibly take O(n) squared?
So that's at least n squared, right? Because you will do n squared times number of swaps that you actually do. Because note that it's not enough to check each pair only once, right? Because what could happen is that you have this child I and j pair. Okay. So I and j maybe get swapped at some point, but then maybe I get swapped with somebody else. So some I prime, j gets swapped with somebody else. Okay. And now I gets assigned what I prime used to get assigned, and j gets assigned something else. And now maybe swapping I and j is like, will again improve it. So actually, yeah, so if you just do local search without thinking, then it could really take a lot of steps. So it's actually tricky to come up with examples where it takes exponentially many, but it's known that there are examples where it takes exponentially many steps. So, alright, so, right, but we don't care that much about it because we assume that in whatever application we care about, local search is easy to do. So let's assume that this is you are able to do this, and you stop if you are no longer able to improve the solution. Alright, so now, how do you argue whether this is any good? So that's what we're going to see. We're going to see that any solution which is locally optimum is not too bad compared to the globally optimum. Okay, so that will be the goal for today. And let me write down formally what does it mean formally what does it mean to be locally optimum? Right? So, and this is what I wrote down. So if you denote by sigma I the gift to child I, okay, so this is a solution is now given by sigma 1, sigma 2, sigma n. The n children. Sigma I represents the gift to child I. Okay. So this is basically how you express a solution. And this solution sigma is said to be locally optimal if you have this condition. Right? Like the value of I to sigma I plus j to sigma j is more than what you get from swapping. So this is the objective value when you swapped. Okay, so any question on this? I just wrote down that condition just mathematics. No. Okay. Alright, so this is what we have if your solution is locally optimal. Now I would like to claim that any solution S in which swaps do not increase value has a total happiness value that's at least half the total happiness of the optimum solution. So this in some sense is a factor 2 approximation to the optimum solution. So that's what we would like to claim. Okay, so in some sense, local search may not be optimal, but it's not too bad. All right. So now there's the usual question: how do we reason about optimum that we don't know? Okay. We've already done this before. Assume that the optimum is something and try to reason about that. Right. So that's the standard trick. And but the main kind of hint is, you ask, can we miss a very high weight edge, right? So remember, if you remember in the greedy algorithm, this is what had happened, right? Like in the greedy algorithm, you had this very high weight edge that you somehow missed because the greedy algorithm missed this edge. Right, so let's start off with asking that question. So if you had any edge of weight some W, okay, and what I would like to claim is that in the optimal solution, not optimal, sorry, in the solution S, okay, let's say your solution S was given by sigma 1, sigma 2. So in your solution S, child I was given this gift sigma. So as we did before. And what I'd like to argue is if I take any edge, so this is between some child I and some gift J. Suppose child I had a very high happiness value for gift J. What I would like to claim is that whoever I was assigned to in this solution, if sigma I was equal to J, then you are in great shape, right? So that means that your solution already picked that pretty large edge. And otherwise, so I was assigned to somebody else. So that's fine. Now, but gift J was assigned to someone, right? Because you know that every gift is assigned to somebody. Okay. So we don't have a name for that, but let's call this person sigma inverse of J. Okay. Okay, so this is some value L with the property that sigma L is J. So this is some L such that sigma L equals J. So L is the person who was assigned the gift J in this locally optimal solution. Now what I would like to claim is that, this is actually a very simple observation, is that this value from I to sigma I, this value J sigma is at least this W. This is actually a very simple fact, but I'm just saying that this was one very high weightage. Now I look at, I define sigma to be the gift that child I was given, and I also look at the child who got gift J. And because this solution was locally optimal, okay, if I take these two children and swap their gifts, okay, so I was given sigma I, L was given J. If I swap the gifts, then means like I'm giving J to child I and the gift sigma I to child L. And I know that all happiness values are non-negative. Right? So local optimality, so this is the claim. Now proof of that is that local optimality is that I sigma I L J are equal than equal to plus and this one is bigger than or equal to 0, so this thing is bigger than or equal to 0. Okay, so this is the proof of the claim. It's a very simple claim, but some of you may have questions about the notation, so feel free to ask. Okay, so all I'm saying is that if there was some edge which had a high weight, then I look at the current happiness value that this child I is getting. I look at the current happiness value that L, who was the child who was currently assigned J, is getting. I'm claiming that sum of these two happiness values is at least the weight of this edge. And the reason is that if not, you could have swapped and you would have obtained a better solution. Okay. So if this were not true, then you could have obtained a better solution, which meant that this was not locally optimal to start. So yeah.
But over here, L would also have been assigned a gift, right?
Yeah, so I'm assuming, I mean, L is defined to be the child who got the gift J. Okay, so in your solution sigma, L was assigned J. Okay, so these dashed lines are your solution.
But now it got assigned to sigma of it, and we didn't add that for our.
So I'm just defining sigma L to be J, right? So L is the L is the child for whom sigma L is equal to J.
Yeah, but you gave that I child another gift. Okay, now you cannot give him.
No. So I originally, so the main challenge in this solution is always the notation. Okay, so let's get that straight. Okay, so what is sigma? Right, so sigma is the locally optimal assignment. Okay, some locally optimal assignment. And sigma is, let's say it's shown in green. So in this picture, I was assigned sigma. Okay. If I was already assigned J, then you would have been done. Okay, so that's what we wanted to show. But so you assume I was assigned to some sigma I. But you also know that J was given to someone, right? Because every gift is given to some child. Okay. And let L be that person. Okay. So by definition, sigma L is equal to J. Okay. That's why I'm also denoting L as sigma inverse of J, because it's like the inverse map. So that's what I'm doing here. So L was the child who got J. Now I'm claiming that in this locally optimum solution, the happiness value of I plus the happiness value of L was at least this edge weight. Okay. And it has to be that, because otherwise swapping the gifts of these two meant that J would have been given I, and this would have gotten a non-zero value. Okay, it would have gotten a value that's at least that's non-negative. So the fact that you did not swap, the fact that that was locally optimal, means that the current happiness value of I plus the current happiness value of L is at least the weight of this edge. Okay. So that is the argument, that you don't miss any very heavy weighted. Okay. So I mean, you're not claiming that this edge is in your locally optimal solution. You're just saying that there are two children whose happiness values add up to at least the weight of this edge. Okay? So it's not a very terrible solution. Okay? So that's that. Yeah.
So are we assuming that number of people and number of fields are equal?
Yes, of course. So the problem statement was always there were exactly, you have n children and n gifts. Yeah. Yeah, but that's a good point. So every gift is given to some children. Yeah.
Are we assuming that the number of people and gifts is even and like are even?
No.
So
They could be.
with some gifts that are not going to be able to swap.
No, so you are not swapping by dividing them into pairs. You are trying to swap every possible pair. Okay, like 1 is swapped with 3, one, you try 1, 2, 2, 3, 3, 1, right? All possibilities.
Okay.
Yeah.
So you will just set the limit for the local and do all the possible combinations.
Exactly. Yeah. That's why it's expensive. I mean, that's why it takes a while. Alright, so yeah.
How can there be a solution with there is no swaps available to increase the value and it's not an optimal solution?
Right, so that's what actually it won't be in your homework because it was on the homework last year, but yeah, so you can easily come up with solutions where actually let me see if I can come up with one on the slide. But you can have things where the costs are slightly off. Okay, so assume that all the edges that I did not draw are actually 0. Okay, so I think my erasing. Okay, so let me draw this again. So you can have solutions where so this one I claim will be a locally optimal solution. What are the other edges? The other edges are the 2 here and the 2 here. Okay. And edges I didn't show are all 0, let's say. Now consider a solution where you just have these horizontal edges. There's no incentive to swap 1, 2 because swapping that would mean 2 plus 0, which is the same as 1 plus 1. Same with 2, 3, and same with 3, 1. So there's no real incentive to swap any of these guys. In fact, you can have this edge also being 2. And yeah, so now there's no incentive to swap anybody. Yeah, actually, I will draw this example and wait for a little while because you should think and convince yourself that there is no incentive to swap because swapping doesn't increase the solution at this point. But still, this is a factor 2 worse than the best solution. So the green is what I claim is a locally optimal solution. And all edges that I did not show, like 1 to 3 and 2 to 1 and so on, these are all 0. So, yeah, let me pause a little bit. I see some people. Yeah.
So how can we come up with the claim that it has a factor of 2? Why it's not a factor of 3 or 4?
Yeah, we will see that. I mean, right, so far I'm just saying that in this example, okay, the optimal, I mean, the locally optimal solution is not globally optimal. Okay, that's the question that she had asked, right? So I just came up with an example where locally optimal solution is quite good. And you need to see why that green solution, which is the 3 1s, is locally optimal. And yeah, the reason is basically there is no incentive to swap 1 and 2 because their total happiness value is 2. Same with 2, 3, and so on. But then globally, there is still a much better solution. globally the solution that does this, this, and this would have an objective value of 6 as opposed to just 3. So this is a simple question.
If those rates were 9, instead of 2, if those rates were 3,
Then you would swap, yeah. Then you would actually swap, and you will actually, at least you'll swap the first 2, right? And so you will assign this to 1 and so on. And afterwards, who knows? You have to carry it out to 3. Yeah. Yeah, you'll probably swap at least 1 more. You might even end up with optimal solution.
So if the bigger diagonal was 3 instead of 2 or even 4, right?
Yeah.
We actually don't swap in the local expression.
Why? Because yeah, actually that's a good point, right? So why? So what he's asking is, what happened if this 2 was equal to 3? So if this 2 was equal to 3, and you were assigning 1s, right?
No, I mean the bigger one.
What do you mean the bigger one?
So we have 3, 2, right? We have
Biggest edge with the weight 2.
so 1 from the left to the right.
This to the right?
No, we have 3, 2, right?
No, initially all of them are 2s and 1s, right? In that example that I drew.
Yes. Yes.
So what do you think?
So we have one bigger diagonal, right?
There's no notion of a bigger and smaller diagonal, right? I mean, these are just edges.
The distance.
There's no geometry here. This is just a graph. I mean, this is just a graph where.
No, I mean the one that I mean.
You mean? So you're just saying, don't look at this edge. Everything is symmetric. That's what I'm trying to say. So if you had, I mean, this edge is no different from this edge. it's just renumbering the vertices.
But it can be 3, right?
Yeah, I mean anything can be 3. Yeah. So if you really want, I can label this one to be 3, and this
So
one.
I mean, if this one is 3,
Yeah.
then the global solution, global optimal solution,
Yeah.
right, includes these 2 and that 3. These 2, 1 and that 3, right? These 2, 2 and that 3, right? Which is 7.
Yes.
While the local is 3.
Yeah, but the
That
local
is
one
not-
is not optimal. That's what I'm saying. Yeah. So the local one is not optimal because now what you would have seen is that, you know, if I took these 2 edges and if I took child 1 and child 3 and swapped their gifts, right? Now I would get a total optimum of 3. Yeah. But if you thought this was asymmetric, then you should rework this example. Okay, there is nothing special about that edge versus any other. Yeah. Any other questions? But yeah, think about what happens if some of the edges are 3 and so on. Okay, so that's a good way for you guys to build intuition. Right? Okay, so now let's try to show this claim more formally. So right now all I have said is that if I take any edge, okay, then I look at actually the locally optimal solution, then the happiness value of this I plus the current happiness value of this L is at least the weight of that. Okay. So let's now use that to show that the total happiness of this locally optimal solution is at least half the happiness value of an optimal solution, which you don't know. Right? So let's define some more notation. So S we already said is sigma 1, sigma 2 to sigma n. And let's look at the optimal solution and let's call it something else. Let's call it gamma 1, gamma 2 to gamma So in the optimum solution, child I is assigned gift gamma I. Okay, that's what I mean. Now I claim that I can proceed exactly as before, right? So what would I like to show? So the claim, if I just translate into notation, is just equivalent to saying that V1 sigma 1 plus V2 sigma 2 Vn sigma n is at least half of V1 gamma 1 correct? This is just the claim just written down in this notation of sigma and gamma. This is what we would like to show. Alright, so now how do we plan to show this thing? So any ideas how you would like to show this claim? Okay. In fact, I mean I would like to show that the left side is at least half the right side. So any guess? Like going by the idea from the previous slide, which is something over here, right? Can you say that this quantity you have a half the y to okay, yeah. So what's saying is, yeah. So this is equivalent to showing that this is these 2 times this. Okay, so these two are the same.
And with this claim, you say V1 plus V2 sigma 2 should be larger than the y.
Yeah, so I guess what he's trying to say is that, so in the optimal solution, let's say 1 was assigned to gamma 1. And in your locally optimum solution sigma, 1 was assigned to some sigma 1. And somebody else was assigned gamma 1. So, oh, I should draw. And somebody else was assigned gamma 1. And by what I saw, what I said before, the sum of the 2 green edges is at least the weight of the black edge, right? Is what we spent last slide on. So what we have is that sigma 1, V of 1 sigma 1 plus V of this value, I was calling it sigma inverse of gamma 1. V of sigma inverse of 1 dot 1 is bigger than or equal to one. So this is nice, right? So I've taken the first term on the right, and I've bounded it by some 2 terms which look like terms on the left. So similarly, I can write V2 of gamma 2 is less equal to V2 sigma 2, V of sigma inverse of gamma 2, and so on. And you can sum up on the left and you can sum up on the right. So the right sum is exactly what you want. It's sum over I, V, I, gamma I. And the first sum on the left is kind of nice. It's just sum over I, V, I sigma I. Second sum is at least seems to be a bit more messy. So it's sum over I of V of sigma inverse of gamma I over gamma. But what is the second sum? Yeah. So can you now reason about it and say that this is something? Yeah, so this is actually exactly the same as the first sum, because what is the second sum in the picture, right? So pictorially, the second sum is basically saying I look at gamma 1 and I add the weight of the green edge going out of gamma 1. And then I look at gamma 2 and I add the green edge going out of gamma 2. Okay? And so on. Okay? And I'm doing that over all the gamma 1 through gamma n. Okay? But that's the same as adding the weight of all the green edges, because every green edge shows up exactly once. Okay? So think about this a little bit. Also, maybe I should have drawn a green edge, not a blue edge. Okay. I wanted to draw a green edge with a red cross. So that's what we're doing. Okay, in the second sum. So that's why this is also exactly the same as sum of all the green edges, which is exactly the same as this term. So then you basically get that this is equivalent to sum over I, V, I sigma I, equivalent to I, gamma. Okay, and this is exactly what we wanted to show. Okay, that twice of the sum is more than the sum with the gaps. Okay. So it's basically the only thing confusing about this proof is the notation. So you'll have to go and work this out with some example, and you will see why. Okay. So, but this is the idea of the proof, like that you basically show that any edge in the optimal solution, you can essentially upper bound it by the happiness value of two people in your original. That's why the locally optimal thing cannot be too bad. And in fact, you can extend this a little bit. You can say that if instead of just checking pairs of vertices when you swap, if you look at triples of vertices, then you actually get something which is at least 2/3 the optimal solution. If you check 4 tuples, then you get 3/4 and so on. Okay, so the solution can be made much better by doing more complicated local search. But we won't get into that for now. But but this is something that is simple. All right. So you should look at the notes for details on this. But the point you should remember is that local search is not optimal. In fact, we saw an example where it was like factor 2 away from optimal. But that's the worst case. Okay, so it can't be much worse. So that's what this theorem is saying. All right. So any questions on this? Yeah.
So, how do you come on factor of 2 in the claim? So,
Oh yeah. So that, because I mean, I wrote it because I only know, right? But if you were going to come up, then you first come up with this argument. Okay. So you first come up with an observation like this. And then you say, okay, I could now let W range over all the optimal edges. Basically, the proof gives the claim. I mean, there is no way of coming up with a claim without actually
we should
doing
come up with some example and find.
Yeah, right. Yeah. That's usually how you come up with these things, because yeah. So in this case, I would have come up with it by thinking like this. So that's why I present it like this, because intuitively what you should think is, can we miss a very high weight edge, right, in the solution? And what this is saying is that you could not have missed a very high weight edge. And that's how.
So you come up with factor of 2 and think that, okay, we are good enough, because factor of 2 is not that much bad, right?
So in this case, yeah, I mean, depending on your application, factor 2 may be very bad, but in this case, we are happy with the factor 2.
So
yeah.
the question is that if you come up with factor of 10, how we can say is it good or bad?
Yeah, so you can't. There is no qualitative. So is this question clear? So he's asking a more philosophical question about factor 2 sounds nice, but is factor 10 also something considered okay? Right? This depends on the problem. Okay, so there are, I mean, in theory, to judge the value of a result is always a tricky thing, right? And often you judge it by a baseline, right? So is there a trivial solution? Like the greedy solution, does it already give 10? If so, then it's not very interesting to do something more complicated and get 10 again, right? Or, I mean, that's how you judge. Okay? So you compare with simpler, more obvious things. Okay? So in this case, greedy was not giving anything. So that's why 2 is still fine. So in this case, I would have argued that 10 is still fine too, right? In fact, in the set cover, we argued that log n is fine. Log n can be pretty big. Right? So yeah, but that's a good philosophical question that you should think about. Yeah.
And that example, this problem was caused by the fact that we had some weights equal to 0.
In this example, yes.
Yeah, if we don't have, if we our weight are positive, we don't get such situation.
Yeah, I would guess that it's still possible to come up with a bad solution. I'm not sure if it's, yeah.
But in that case,
Yeah, in this example, it doesn't work. Yeah.
Equality between S and of the total happiness of
Right. This example doesn't work, but I would guess that there are other examples. Yeah, you can imagine changing the 2 to 2 minus epsilon and put those guys to be epsilon and probably. So, yeah. Then the optimum solution will be worse, I don't know. Yeah, but you should check. That's a good homework problem.
So in the query you use 2 value is larger than W plate.
Yes.
In this case, we ignore the other part.
Right.
And increase is 0.
You're saying that the only reason this argument can be tight is if these weights are 0. You're right. Yeah, so you cannot have. That's a good point. Yeah. So do you guys see what he's saying? So what he's saying is, in this bad example happened just because some of the weights were 0. But suppose I was promised that all weights are at least, I don't know, 0.1. Then can you get a better approximation ratio? And I think he answered his own question, because what he said is, yes, you can, because the way we made this argument was somehow that like this, not this argument, the next argument. The way we came up with the factor 2 approximation is you had this plus this other term which you ignored. Okay. So this argument is only tight if those other terms are all 0. Okay. So if you had a slightly better way to bound thing, then you'll get a better. Yeah, maybe that's a good homework problem. If all the weights were between, if all weights are between, let's say 0.1 and 1.0, then you can actually get a factor better than 2. Okay. So this is something that that you can try. Okay. So So maybe I put it on the makeup homework because I've already done homework for this part. So yeah, but it's good for you guys to think. Okay. All right. So any other questions? Okay, great. So let's. So I wanted to do a brief recap because I think this marks a time in the course where we've done like a few basic tools. Okay, so what have we done? Right. So seems like there's more done than left, but that's not true. Right. So what we've done is we've covered some of the very basic tools. We've done divide and conquer, and divide and conquer algorithms. Usually you do it via recursion. You implement them as recursive algorithms, and analysis is often done by induction, and running time analysis is often done by writing down recursions. Okay. So that's what. So that's generally how we go about this. And dynamic programming, I said, is should think of it as doing some kind of a recursive formulation, but you observe that the number of sub-problems you're trying to solve is small. That's what we saw. And so you store answers for problems. And then we said, okay, there are greedy algorithms, there's local search, stuff like this, which are somewhat natural paradigms. And yeah, often these kind of algorithms are easy to come up with and implement. And they're harder to reason about than, let's say, dynamic programming or divide and conquer, where usually a very standard inductive procedure just works out. So here, I mean, there were lots of questions about how I came up with certain claims. Like, if you remember in the set cover, somebody was asking this question of why does the set size, why do you look at this particular quantity? And that's very important to the proof. So that's why greedy algorithms, local search, these are tricky to reason about, but they're often easy to come up with. Alright, so these are things we've seen. And in terms of basic paradigms, we'll see a couple more in the course. But I think before we go there, let's use some of the ones we've seen to come up with some algorithms for some simple graph problems. Okay, so that's what we'll do this class and the next. Okay, and yeah, and then after the break, we'll do something about randomness operations. All right. So today I wanted to come up with algorithms for this very basic problem, which is finding the shortest path. So we saw this problem before. Okay, so the problem is just you're given some graph, and let's say it's a directed graph. So going from place A to place B could take longer than coming back. Okay, so you're given some directed graph, and you have some edge lengths or edge weights, and your goal is to find the shortest path from U to B. So this is a standard maps problem, right? You want to get from place A to place B using the shortest possible path. Alright, and so we said before that you could have exponentially many paths. Just searching all paths. Actually, enumerating paths is pretty difficult in itself. So it's difficult to do that. So earlier when we were looking at dynamic programming, we saw this algorithm which is called Bellman-Ford algorithm. But here we had an extra parameter, if you remember, which we called the number of hops. Okay, which is the number of vertices you go through to go from U to B. And that was a parameter, and then we said that that you could write a recursive formulation for going from U to V using some L hops. And this could be written as, you want to get to some neighbor of V using L minus 1 hops, and then you have to get to V. Okay, so that was the idea that we used, and we had a dynamic programming formulation that was based on this idea. And there were these sub-problems. basically look like length of shortest k-hop path from U from some W. So these were the subproblems. And we saw that this had a running time which is L times M plus N. Okay, where L is the number of hops. And note that you can use this problem to solve that as well. So the only difference between this and that is that there is no L in that problem. So L could be anything. So what is the range of L that you have to search for? Yeah, so what he's saying is that you don't have to go for L being more than N, which is the number of vertices. You remember N and M are always what we use for size of V is N, size of E is N. So he's saying that you don't have to, you never use number of hops that is more than N. And that's clear because if you use more than N hops, you must have visited some vertex twice. Okay. And if all the edge weights are positive, then you don't have to do cycling. So a shortest path can never have a cycle. So that's why this algorithm itself gives something like an N times M plus N running time. Problem. Solve this problem from start. So this is fine. This is polynomial, but this is still not that great, right? I mean, you would like to see if there's something better that you can do. Right? But so is this solution here? It's just a sanity check. This is what we've done before. So and the question is, can you do better? Okay, so can you do shortest path and something better? And the question you've got to ask yourself, one question is, what about unweighted graphs? If you don't have edge weights, right? So I tell you that every edge is of length 1. So this is just some unweighted directed graph. That give you some U and V, and ask you to find the shortest path. So how quickly can you solve this problem? All edge weights are 1.
We'll go maybe the shortest way to the last edge.
Correct, but what is the, how do you find that?
Shortest path first, maybe.
You try to solve that, right? Okay. So if your graph is unweighted, then you can just do this breadth first search, right? And what is breadth first search? It's just you start with U, you explore, you see everyone who is reachable with one edge. Okay. In this case, there are only those two vertices. So this one and this one. And you see everyone who is reachable with 2 vertices. You see this one, sorry, 2 edges. Okay. And in some sense, you go breadth first outside, right? So breadth first just means that you explore all the edges that could now go out of these vertices. In this case, you get this, you get somebody up here, and you also get the edge back, but you've already visited. This is your start vertex, so you've already visited this vertex, so you don't take that. Okay. So these were all things that you reached at level 1. Okay. These two vertices were the ones that you reached at level 2, and these three vertices you reached at level 3. And then you look at all the neighbors of these level 3 vertices and so on. Okay, so this is just basic breadth first search. And this will find the shortest path, but the moment you hit V, you will know the shortest path. Because it's just growing in some sense a region around your vertex of increasing radius. Right? So you think of it as growing a region around you of increasing shape. Okay. So this is and how long does this take?
Just the number of edges.
Right, so this is just, this is basic breadth first search. So each time, each edge is explored exactly once. Right, so it's number of edges. So let me write n plus n because you see every vertex also and you maybe do some processing. Okay. Alright, so this is the running time of basic breadth first search. Right? So this is much nicer, right? This is a factor n better than this. So here it was n times m plus n, now you're able to do it in only m plus n. So you save potentially a factor that depends on the number of vertices in the graph, which could be huge. And now the question is, can you do this in more generality? So the idea here was basically you start with some vertex and you slowly grow this region of increasing radius, right? And does this make sense in a general graph? So here it was nice because you could say everybody at distance 1, everybody at distance 2, everything was growing in increments of 1. So can you do this for arbitrary, how would you do this for arbitrary graphs? So this is the question we would like to ask. Okay, so can you construct a ball of a certain radius around a certain point? Okay, so so actually this makes intuitive sense in contexts like maps, right? This can be an arbitrary graph where edges have some weights and so on. Like getting from here to here takes some time, something. Going from here to somewhere else takes someone. And this is a complicated graph. But this notion of what is at a 5-minute radius around you makes intuitive sense. So how, and in this graph, for example, if so this is not directed, but let's assume that it's bidirectional. So in this case, if this was your view, if I tell you what all points are at distance less than equal to 20 from you. So this makes some sense, right? Like this one is at a distance 7, this one is 10, this one is 20, this one is some 14. So there's a bunch of vertices that are flooded. There's this guy. And in this example, maybe there's nothing else. Right? So this notion of a ball of a certain radius is pretty well defined, even if you have a weighted graph. Right? Like ball of radius 1 maybe is empty around this, it just has this one vertex. But any other radius, it's a well-defined point. Alright, and actually one thing that I would like to mention is that, so this is something very common. It is common to think of graphs as what are called metrics. How many of you have seen the word? I've not seen the word metric before. Oh, okay. So does that mean all of you have seen it, or none of you have seen it? So a metric is just a distance function. Okay, so it's nothing fancy. It's just a distance function, and very often people think of graphs as metrics because the shortest path in a graph, it behaves as what is called a metric. Okay, so it's just a distance between u and v. The important thing is that this satisfies triangle E of u v plus d of v w is bigger than or equal to d of u. And you can see that this is true for shortest path functions. Right? Like if you can go from u to v with a certain path length, v to w is a certain path length, then the shortest path from u to w is at most the sum of those 2 points. This is just because you can there's at least one path of that. Yeah.
Symmetry.
Yeah. So usually a metric is symmetric. In directed graphs, this is not. Yeah. So yeah, you have to. Yeah. Yeah. So I'm defining metrics to be asymmetric. All right. So this is the definition of metric. And now, suppose I ask you, can I construct a ball of a certain radius and slowly expand that radius? Okay. So that's the idea behind this algorithm. It's called Dijkstra's algorithm. So the other thing is, the other main observation that you've got to remember, this is also an easy observation, is how can you have a path of length r from vertex u to some vertex v? So you either have an edge of length r, or you have a path to some vertex that's at a distance less than r. This is a distance less than r, followed by this edge to b. So this is another obvious fact, because all distances are all edge lengths are bigger than 0 in our set. Right? So this is the only way you can get from vertex u to vertex v. Alright, so now using this very seemingly trivial observation, how do we now grow a ball of a certain radius r around a vertex u? Okay, so let's see how that is done. So let's take a simple example. So we have a vertex here, and you have a ball of radius. So these are all. So let's say this is 4. This is 5. So these are all vertices at a distance of 5 from you. Now, let's say there are no other vertices that way. So now, suppose I ask you, what is the next closest vertex? So think of slightly enlarging this ball to include one more vertex. Now, is there an easy way to find that vertex? Yeah,
It would be just the minimum edge coming out of the ball.
So what his suggestion is, look at the minimum edge that's coming out of the ball. So look at all the edges that go out of the ball. And look at the least weight edge. Okay, and his claim is that that would be the next vertex. Do you guys agree? So if I had to, actually, do you guys see what I'm trying to do? So I have this ball, this is of radius 5. I'm trying to slightly enlarge the ball so that I include exactly one more vertex. So maybe it won't be exactly one, but it should be so that all the vertices included are at exactly that radius. But just assuming all distances are different, just think of exactly including one more. So what would be the next closest vertex to you?
Probably the vertex attached to you.
Sure, but what if this length was 100? But that's a good suggestion, right? So your suggestion is, yeah, it should be close to you. His suggestion goes in the opposite direction. His suggestion is, let's look at, let's say, the smallest edge weight. So if I have weights like this, and let's say I had, this one was being, actually I'm going to mess up what he's saying. So I'm going to have 2.5 here, okay? So what his suggestion is that one of the twos is the closest one. Okay? But you can see that in this example, one of the twos would not be the right one because this one was at a distance 5. So if you follow the edge there, it would be length distance 7. And this one would be a distance 7, this one is a distance 100. But this one, if you follow that, it would have been 6.5, right, which is less than 7. Right? So it's not just the length of the edge out that matters. The length definitely matters to some extent, but it's the length of the path out. Right? So you look for the vertex. So let's say you have the current ball, which is S. Okay, let S be the current ball. And now for all the edges of, let's give them some name. Let's call them IJ. Out of S. Compute distance from U to I plus the length of the edge IJ. Okay. So this is, in this example, this would be like 4 plus 2.5. And for this one, it would be 5 plus 2. So this is one candidate IJ. This is some candidate I find. So that's what I mean. Okay, so for every edge out, you compute distance from U to I. This is a quantity that you already know, right? So I is some vertex that was inside S. Okay, and J was the vertex that was outside. And I'm trying to compute this one. And pick the J that has the least value, least such value. You add J to S. And I claim that now I have found, so I haven't formally written down the claim here, but it's the algorithm here. So this is just simply, you have the set of vertices that are at a certain radius, and now you look at all the edges that go out. So I is inside and J is outside. Of those, you pick the J that has the least value of this distance from U to I plus the length. And I claim that that is the closest vertex outside of S to this vertex. Let me read that. I haven't proved this, so I'm going to show this. Okay, it's simple, but I will have to show. So is the procedure clear to everyone? Yeah, and I am assuming that I am storing these values and so on. Okay, so let's not worry about implementation at this point. Right. So let me first show this claim that J is the closest vertex to S outside of S to this. And the way you prove this claim, such claims, is by contradiction, right? Like if there is a different vertex J prime that's closer to U. So let's take any vertex J prime that is closer to U. So there must have been some path. So let's do this contradiction in a different color. So there must have been some path going from this to this, okay? And in particular, there must have been some point where this path left the set S. Okay. So let me just write it out. What I'm saying is very simple, but so proof is by contradiction. Let me write out the steps because we are almost out of time. It's like let J prime closer point if possible. Okay, then look at the path from U to J prime. And what we'll argue is that if you looked at the path from U to J prime, you will get that there was some vertex in the path that you would have considered, and that would have been a better thing than J to add in your procedure. So this contradicts the fact that your procedure was always adding the quantity with, adding the J with the least value for this quantity. Okay? So this is the idea. So since we are out of time, let me stop here. I'll come back to this next time. We also see other arguments.